Welcome to This Explainer. Today, we're diving headfirst into a really fascinating benchmark test taken straight from a developer's journal, specifically a post called Notes-on-Haskell-Programming. We're tackling a massive debate that has sparked, well, probably countless arguments in forums and code reviews everywhere. Basically, when it comes to writing Haskell, is it actually worth sacrificing clean, beautiful, human-readable code just to squeeze out a tiny little bit of extra performance? We're going to follow the author's exact experiment to find out. Okay, let's get into it. We've all been there, right? You write this gorgeous, simple function. It makes total sense. It practically reads like plain English. But then, that little voice in the back of your head pipes up. You start wondering, should I rewrite this? Make it a bit more cryptic? You think maybe if you manually manage things, you can squeeze out some extra speed? Or actually, scratch that, maybe you're just terrified of memory leaks. So you introduce all this complexity because we kind of assume that dense, explicitly managed code automatically equals better performance. And this brings us right to a classic developer dilemma. It's essentially two totally different philosophies going head-to-head. On one side, you've got ugly but fast, this slightly crazy assumption that intentionally writing verbose, complex code that micromanages everything somehow makes your program fly. And on the flip side, we have readable but slow, the desire to keep the code base clean and understandable, but constantly carrying around this lingering fear that we're sacrificing pure computational horsepower to do it. So let's meet our contenders and look at 3 different ways to count. To actually test this out, the author set up a benchmark. The task? Count the volume headers hidden inside a mock list of 100,000 text blocks. It's your classic data parsing job, perfect for seeing how different styles handle a big chunk of data. Step 1 is the original approach, a highly readable, super straightforward list comprehension using the length function. Step 2 is our ugly but fast contender. It's a complex rewrite using an explicit, strict foldl function, which was specifically designed to skip intermediate values and block memory leaks. And finally, step 3 is a middle ground alternative. A list comprehension but using sum instead of length. Same exact problem, 3 totally different ways to solve it. All right, round 1. We are starting off in the unoptimized interpreter, GHCI. For this first test, the author ran all 3 methods through GHC's raw interpreter. Now, doing it this way gives you fast compilation, which is awesome for quick prototyping, but you aren't using the compiler's full horsepower. And wow, talk about a plot twist. Look at the bar for that explicit foldl approach, the one meticulously written to be faster. It was actually the slowest by a mile, clocking in at around 13 milliseconds. Meanwhile, the original readable length code totally won the race at just under 9 milliseconds. The sum approach just kind of chilled in the middle at about 9.2. Think about what this means. Running completely unoptimized, the simple, readable approach was already smoking the clever rewrite. The author points out that this shows the original code was already being handled beautifully by the Haskell setup. Trying to optimize it with that explicit foldl did absolutely nothing to help. Literally all it did was clutter up the codebase with cryptic, wordy junk that's harder to read. But we can't call the fight just yet. Round 2 brings in the -02 compiler flag. Compiling this benchmark into a native binary using the -02 flag is like flipping a magic switch. It unleashes a massive suite of optimisations directly onto our code. We're talking heavy-duty stuff, worker wrapper transformations, unboxed primitives, aggressive inlining, and a really cool one called list-fusion or deforestation. I know, those sound like terrifying textbook terms, but basically, it just means the compiler is doing some incredibly genius housekeeping for us right behind the scenes. Now let's look at the natively compiled numbers. The playing field hasn't just changed, it is completely 100% leveled. All 3 approaches are now performing essentially identically. The explicit foldl is sitting at roughly 280.4 microseconds, sum is at 280.8, and the original length code is right there at 288. You basically can't tell them apart. I really want to pause on this number for a second. 280 microseconds. Execution time for all 3 methods just completely plummeted from around 9 to 13 milliseconds, all the way down to a fraction of a single millisecond. That is a massive off-a-cliff drop, and it perfectly illustrates the sheer brute force power of a modern compiler when you just step back and let it do its job. So what's the secret weapon GHC is using here? It's called stream-fushion, also known as list-fusion or deforestation. What happens is, no matter how wildly different your code looks on the screen, the compiler looks at all of those approaches and just automatically flattens them into the exact same highly optimized loop. You tried to be super clever with foldl, and the compiler essentially patted you on the head and said, yeah, I know what you want. I'm just going to optimize the readable code to do the exact same thing anyway. Now, I know some eagle-eyed viewers are probably yelling at the screen right now, but wait, the foldl method actually was a tiny microscopic fraction of a microsecond faster on that chart. And yeah, technically, you're right. But as the author points out, at this level of measurement, those ultra-minor differences are absolutely meaningless. You are literally just looking at random noise and system jitter on the testing machine. It's not a real statistical advantage that's actually going to speed up your app. Which brings us to our final verdict. Seriously, trust the compiler. So what does this whole dramatic benchmark showdown actually teach us about our day-to-day coding? The author sums it up perfectly right here. The original list comprehension approach using length and unit is adequate with good readability and conciseness in the first place. You really don't need to reinvent the wheel. The clean, readable version gives you phenomenal performance right out of the box simply because the tools we're using today are smarter than ever before. There is a tiny caveat, of course. You should only ever reach for that alternative sum approach or the really explicit foldl method if you are in a highly specialized situation where you desperately need to squeeze out a fraction of a microsecond of performance. But for 99% of what we do every day, it is absolutely not worth destroying the readability of your entire codebase for it. At the end of the day, modern compilers genuinely have your back. They're doing all the heavy lifting and optimization for you entirely behind the scenes. So I'll leave you with this to chew on before your next code review. Are you finally ready to stop endlessly over-optimizing, trust the tools sitting right in front of you, and just start writing clean code that humans can actually read and enjoy? Thanks so much for hanging out with me for this explainer, and happy coding!